Hey everybody, so this video is about logarithmic functions. Again, this is going to be a quick review of logs. It's not meant to be an introduction, so if you need more resources, check the email that I sent out. Okay, so the first thing I want to do is just remind you of the difference between log form and exponential form. Okay, so if you have an equation that's a logarithmic equation or an equation that's an exponential equation, you can change back and forth between these two forms and they absolutely have the same information, okay? So if you have something that looks like log base b of x is y, you could rewrite that as saying b to the y equals x, right? This is kind of the definition of what the logarithm means, okay? It's the exponent that you raise b to get y as an answer, okay? So we are going to look at just a couple little things with notation, and then we're going to do some examples. Okay, so there are two logs that we use the most. The one that's called the common log, which is log base 10. Okay, and instead of writing log base 10 of x, people will rewrite this as just log x with no base. Okay, so just so you remember, I think I even used this in the previous video. If you don't see a base, that means log base 10. Okay, now if you have the natural log, okay, remember this is log base e. Okay, and instead of writing log base e of x, people will write ln of x. Okay, all right. So now that we remember those two common notations, let's do an easy couple of examples. Okay, so we're just going to evaluate some logs. We'll do one easy one so you remember how to do it, and then we'll do some ones that are more up to the level that we're looking for here. Okay, so we have log base 2 of 32. So remember the question you're asking yourself is what exponent of 2 is 32? Well, we know that 2 to the 5th is 32, so our answer is going to be 5. Okay, so that's the idea. So let's look at some examples that are maybe a little bit more difficult than that. Okay, so the first thing I see about this one is that I have a fraction. And when you think about fractions and exponents, what kind of exponent, oops, there we go, is going to give you a fraction, right? Negative exponents give you a fraction, so I know this is going to be a negative number, okay? And then I'm thinking, well, what power of 2 is 4? It's 2. Okay, so the negative makes this into a fraction. The 2 gives me 2 squared equals 4. Okay, all right. So what about something like this? Okay, where the base is larger than the answer, right? So remember, I'm asking what exponent of 4 is 2? Okay, well, remember, root 4 is 2. So what exponent is the same as square root? Well, the 1/2 power is the same as the square root. Okay, so for that reason, I know that this answer is going to be 1/2. Okay, so let's look at something a little bit more complicated. Okay, so I'm looking to get from 8 to 4 using only exponents. Okay, so what I might say is, okay, 8 and 4 are both related to 2. So let's use exponents to get 8 down to 2, and then we'll move to 4. So we're going to do it one step at a time. Okay, so the first thing is, what exponent of 8 is going to be 2, right? So we know that this is the cube root, so that's going to be the 1/3 power. Okay, so our first step is going to be the 1/3 power. Okay, and then when we have 2, we want to move to 4, so we know that's going to be a square. Okay, so our second step is this 2 power. Okay, so we're going to have 1/3 and then 2. We multiply them together to get 2/3, right? If you don't believe that, 8 to the 2/3 power, right? That's going to give you the cube root of 8, which is 2. 2 squared is 4, right? That's the lines that we're thinking along. Okay, let's do another example like that. Okay, so we have the same kind of thing. If we have 9 and 27 are both related to 3. So first we want to get from 9 to 3. So that's going to be the 1/2 power. Okay, and then if we want to get from 3 to 27, we're going to cube. Okay, so our second step is going to be to cube it. Okay, so again, we're thinking about these as exponents, right? And this is why we're multiplying them, because if you have one exponent raised to another exponent, you multiply them. So this is going to be the 3/2 power. Okay. All right. So now that we've seen that, let's do one example of solving log equations. Okay, so this is a very specific type of log equation that we're going to solve. We'll solve more general ones in 5.4 when we talk about just like solving these types of equations, but right now we're going to solve just one super specific type of equation. Okay. All right, so the type of equation that we're solving has two logs equal to each other that have the same base. Okay, now this is really similar to what we did with equating exponents, right? Remember what we said about equating exponents is that when you have a one-to-one function, if the output is equal, then the input is equal. Okay, well, logs are one-to-one functions, so if the output is equal, then the input must also be equal. Okay, so again, we can only use this solving method because log is a one-to-one function. Okay, but that's the method. It's pretty easy, but it only works for super specific situations when you have something like this. Okay, all right, let's look at one more example of this. Okay. All right, so again, we're going to say this is a one-to-one function, so if the output is equal, then the input must be equal, so x squared must be x plus 12. Okay, now in the previous example, we had a linear equation, now we have a quadratic, so we're going to factor. Okay, and we're going to get two solutions, 4 and -3. Okay, all right. Now, I did want to point out, even though this solving method is pretty simple, it's important to actually check for extraneous solutions when you're solving log equations. And the reason for that is because you can't plug a negative number or 0 into a log, okay? And I'm worried about that in this example because I actually have this -3 as my answer, okay? So if you look at this one and you check, you would have 6 minus 1, which is 5, okay? So this one is fine, okay? Now if we check this one, 4 squared is 16, that's positive, that's good. 4 plus 12, that's 16, that's positive, that's good. Okay, so we check that one. Here, -3 squared is 9, so that's fine. -3 plus 12, also positive 9, so this one's okay too. All right, so even though we have a negative answer, it's not necessarily extraneous, but you can get extraneous solutions from log equations, so you should check. Okay, so like I said before, we're going to solve a lot more log equations in section 5.4, but that's just that one super specific type that's in this section. Okay, let's talk about some graphing. Okay. So the key features of the graph is we have a vertical asymptote at x equals 0, right? The y axis. Okay, and then we have our key points, which are 1 over b negative 1, 1, 0, and b 1. Okay, now these key points might look really familiar to you, and they should, because these are the key points from the exponential graphs with x and y reversed. Okay, that's not a coincidence, it's not some sort of trick, right? Because exponentials and logs are inverses, right? That means the role of x and y are switched. So of course they have the same key points, but just with the x and y switched. And you'll see that the graphs are the same reflected across the line y equals x, like we know to be true about inverse functions. Okay, also, just to remind you, the domain is 0 to infinity, and the range is everything, okay? Now you can also see that the domain and range are switched from the exponential functions, which again is a property of them being inverses. Okay, so let's look at some base graphs. Okay, so we're going to draw two base graphs. Well, yeah, let's draw two base graphs. Okay. All right. So here our key points are going to be 1/2, negative 1, okay, then 1, 0, and then b, which is 2, sorry, 2, 1. Okay. So we're going to put in our vertical asymptote here along the axis. Okay. Then we're going to graph our key points. Okay. So 1/2, negative 1, 1, 0, and 2, 1. Okay. And our graph is going to have this shape. Okay. So this is our base graph for the base 2. Okay. Now I wanted to show the base graph for natural log because for some reason, even though it's very similar, people get confused about what the e base is going to do. Okay. So remember, the key points are still going to be 1 over e negative 1, right? 1, 0, and e 1. Okay. Now e is like 2.7. Okay. So if you're thinking about where to graph it, you're thinking like, okay, 1 over 2.7, that's close to 1/3, okay? Okay, so we're going to go like 1/3, negative 1, 1, 0, and then 2.7, right, which is E1, like this. And then it has the same general shape. Okay, so it should be a little bit steeper than the previous example just because the base is a little bit larger, but in general, all the log graphs have this same general shape. Okay, let's look at some transformations. Okay, so first we're going to use our first base graph, the log base 2 graph. Okay, so this negative sign is going to reflect it. Okay, and it's because it's inside, it's going to affect the x coordinates. We're going to go across the y-axis. Okay, then this plus 2 is going to move the graph up 2. Okay. Okay, So our vertical asymptote is going to look exactly the same. Okay. And then we're going to reflect each of our points and move them up 2. So the one that was here, we're going to reflect it across and move it up 1, 2. Okay, the one that was here, we're going to reflect it across and move it up 1, 2. Okay, and the one that was here, we're going to reflect it across and move it up. Oops, that was here, reflect it across, move it up 1, 2. Okay, those are our key points. Looks like that. Okay. All right, let's do another example with that base graph. Okay. So here, this -1 is going to move the graph right 1, and this +3 is going to move it up 3. Okay. So let's look at our graph here. Okay. Now, if we're moving everything right 1, that's going to include the vertical asymptote. So we're going to move it from 0 to 1. Okay, and there's our horizontal asymptote. Okay, or vertical asymptote, sorry. Okay, so now we're going to move this point, okay, the one that was at 1/2 -1, we're going to move it right 1, and we're going to move it up 3. Okay, and then we're going to take this point, we're going to move it right 1, and we're going to move it up 3. Okay, and then we're going to take the point that was here, we're going to move it, oh, it was here, sorry, at 2. We're going to move it right 1 and move it up 3. Okay. So this is what my graph looks like. Okay, same shape, just moved over and up. All right, let's look at some graphs with a natural log base graph. Okay, so this 2 is going to stretch this vertically, okay, to double its size. Okay, so remember that means we're going to multiply all of our y coordinates by 2. Okay, so this isn't going to affect our vertical asymptote at all. Okay. Okay, so we're going to take our point that was at 1/2 -1, okay, and then that's going to move to 1/2 -2. Oh, I'm sorry, this is the natural log. Okay, so it was at 1/e -1, okay, and then times 2 is 2/e, okay, so this is our original point. I keep misspeaking and I want to get it right. Okay, so our x-coordinate stays the same, our y-coordinate gets multiplied by 2. Okay, so we're at 1/e -2. Okay, then our second point is normally at 1, 0. Okay, multiply the y-coordinate by 2, you're still going to have 1, 0. So that point's still going to be here. Okay, then we normally have E1. Okay, we're going to move that to E2. Okay, so remember that's 2.72. So that's going to look like that. And we're going to have, ooh, like this. Okay. That loopiness is just from uneven scaling. Okay. So that's how that works. Let's do one more example with the natural log. Okay, so this minus is going to reflect. Okay, and it's going to reflect across the x-axis. Okay, and then the -2 is going to move it down 2. Okay. Now, if we're reflecting, that's not going to move the vertical asymptote at all, okay, and neither is moving it down. So our asymptote is still here on the axis, okay. Okay, so we would have this point that's normally at 1 over e negative 1. So we're going to reflect it across, and then we're going to move it down 2. Okay, we have this point that's at 1, 0. We're going to reflect it across and move it down 2. We have this point that's at e 1. We're going to reflect it across and move it down 1, 2. Okay, and my graph is going to look like this. Okay. Now, I did want to point out that even though this graph looks pretty flat, it will eventually cross over the axis here. It does continue to increase, so pretty far out here, it will eventually go across the axis, so it's not like it's totally leveling off. Okay? All right. So, like I said at the beginning of the video, there are extra resources about this material in the email if you don't have enough here, but I will see you guys soon.